So here we have the analysis of a thermodynamic conversion of heat to work. And in order to do that, again, we need to look at the machine that we're going to use. We need to look at what happens in a particular example in a plot of pressure versus volume. This is the pressure-volume coordinate system, and as we'll see, it's profoundly clarifying in our understanding of the conversion of heat to work. And then finally, we want to look at the first law of thermodynamics. We want to look at the initial internal energy of the system. We want to examine the final internal energy of the system. And we want to look at the terms of heat and work that balance our first law of thermodynamics. So what we need to analyze then is exactly how we progress in the pressure-volume coordinate system. So we're going to start out with an isobaric system. And an isobaric system means that pressure is equal to a constant, and it means that delta P in this thermodynamic act is equal to 0. So we can immediately see what this means for our machine. It means that we've got a particular mass sitting on top of the piston that's operating in combination with the pressure of the atmosphere to fix the pressure that exists inside that machine, that is, the pressure of the gas. And in this particular case, we're going to add heat. We're going to add heat with a laser that produces light energy that's absorbed by that machine, and so heat goes into the system by virtue of the coupling between the radiation from the laser and the metal surface that constitutes the machine. So as we add and continue to add heat by shining the laser on the bottom of this machine, the piston is going to rise because the volume rises, and the volume rises because the temperature is increasing by virtue of the addition of heat. But what does this look like on our pressure-volume coordinate system? It means that as we are adding heat by virtue of the laser, we're moving along a pathway on this pressure-volume surface, but at fixed pressure. Well, this is a very important trajectory because the work is equal to minus P times delta V. Well, this is for the case of constant pressure, but delta V is exactly equal to this displacement. So the work done in this isobaric trajectory is exactly equal to the area under that curve. And this turns out to be extremely important because no matter what trajectory we take on the pressure-volume coordinate system, the work is always equal to the area under that curve that's shown in purple here. All right, but now let's look at the first law of thermodynamics, because when we have an initial thermal energy and chemical energy, first thing we realize is that we don't have a chemical reaction going on inside the system, so we can ignore the term that represents chemical energy. So that means we're going to focus on the thermal energy initially, the thermal energy final. And so let's just indicate we have 1, 2, 3 units of initial thermal energy. But the work done by the fact that the piston has moved up, that means the system is doing work on the surroundings. That means that the work term must be less than 0. And so we have 1, 2 units of work going from the system to the surroundings, so we have minus 2 units. The heat going in by virtue of the laser is going to give us 3 units, 1, 2, 3 units of heat going into the system. And so heat is a positive number because it's going from the surroundings to the system. So if we have an initial 3 units of thermal energy, we're going to subtract off 2 units because of the work that's being done. We're going to add 3 units because of the heat, and the result is we have 1, 2, 3, and 1 more unit of thermal energy resulting from the difference between the heat added and the work done. And so now we've tracked the initial thermal energy, we've kept track of the work and the heat term, and lo and behold, the thermal final energy is a result of that initial thermal energy and the difference between the work term and the heat term. So now we've worked out the trajectory, the machine, and the first law of thermodynamics for our isobaric process. So now the challenge is to work out the same triad, the machine, the PV coordinates, and the first law of thermodynamics for the other trajectories that we need on the pressure volume coordinate system to calculate the relationship between heat and work in a heat engine.